Hello, grade 10s. In today's lesson, we are going to start on the section on the periodic table. And this section is very important in understanding certain patterns that exist on the periodic table. So let's take a look at our objectives. We're going to describe the periodic table as displaying elements in order of increasing atomic number. And we're going to show how the periodicity, meaning patterns on the periodic table, of physical and chemical properties of elements relates to their atomic structure. So this will make a lot more sense once we have looked at the periodicity of elements and how that impacts their physical and chemical properties and how that is influenced by how the atoms are arranged. We're going to define the group number and the period number. We're going to relate the period number to the outermost energy level in which electrons exist. Again, this will make a lot more sense a little bit later on. And we're going to relate the group number to the electronic structure in terms of valence electrons and valency. This is really, really key in figuring out our covalent bonds and ionic bonds a little bit later on. We're also going to describe periodicity, again, patterns on the periodic table in terms of atomic radius, which is the size of the atom, and ionization energy, which is the energy required to remove an electron from an atom. So let's start to take a look at some of the systematic arrangements of the elements on the periodic table. The periodic table displays the elements in increasing atomic number. What do I mean by that? Well, hydrogen has an atomic number of 1, and helium has an atomic number of 2. Then lithium has an atomic number of 3, 4, 5, all the way to 10, starting again here at number 11. Therefore, it is easy to identify the position of the elements on the periodic table based on their atomic number. And this atomic number represents the number of protons in the nucleus of an atom. Remember that the number of protons is what describes the type of atom that it is. That is the definition of the identity of the atom, not the number of neutrons and not the number of electrons. Now, the properties of the elements are also based on the electronic structure of the atoms, meaning the electrons that exist in the electron orbitals around the nucleus. That's because valence electrons, those are the electrons in the outermost energy level of an atom, are responsible for chemical bonding. Recall that valence electrons are the electrons in the outermost energy level of an atom, and the elements in the periodic table are grouped based on the number of valence electrons. What do I mean by that? Well, all of these group 1 elements will have the same number of valence electrons. All of these group 2 elements will have the same number of valence electrons. You'll see soon, we skip the D block. All of group 13 elements have the same number of valence electrons. So that means that within a group, the elements that exist within a group will have similar properties when it comes to chemical bonding. Now, each period in the periodic table starts with atoms with electrons in a higher energy level. What do I mean by that? Let's go to the periodic table. So over here, we have period 1. In period 1, we have hydrogen and we have helium. Hydrogen has 1 proton and it has 1 electron if it is a neutral hydrogen atom, and helium is a noble gas, so it is always neutral. It has 2 protons and 2 electrons. So hydrogens and helium's outermost electrons both exist in the first energy level, which is n equals 1. N equals 1, the first energy level of any atom, can hold a maximum of 2 electrons. So in the case of hydrogen, it will hold 1 electron, and in the case of helium, it will hold 2 electrons. Now, when we move on to the second energy level over here, that is n equals 2, well, that tells us that the outermost electrons of all these period 2 elements exist in the second energy level. So their first energy level is full, meaning that in their first energy level they have 2 electrons, and in their second energy level they have their outermost electrons. The second energy level can hold a maximum of 8 electrons. So in the first energy level of lithium, there will be 2 electrons, and in the second energy level of lithium, the third electron will fit in. In the case of beryllium, in the first energy level, there will be 2 electrons. That means that the first energy level is full, and the second energy level of beryllium will hold 2 electrons. The second energy level of boron will hold 3 electrons. The second energy level of carbon will hold 4 electrons. The second energy level of nitrogen will hold 5 electrons. The second energy level of oxygen will hold 6 electrons. The second energy level of fluorine will hold 7 electrons. And the second energy level of neon will hold 8 electrons. And that makes it a full second energy level. Again, neon is a noble gas. It doesn't want to react with anyone. So we can kind of already see a pattern that noble gases have a full outermost energy level. We're going to come back to this, and we're going to see lots and lots of diagrams that will clarify this. So in the first energy level, there is a maximum of 2 electrons that can be held. In the second energy level, there's a maximum of 8 electrons that can be held. In the third energy level, there's a maximum of 8 electrons that can be held. We need to be aware of these. In the fourth energy level, there's a maximum of 18 electrons, but as already mentioned, we're only interested in the S shell of the fourth energy level. So we're only looking at the first 2 electrons of the fourth energy level, and we're not going to get more complex than that. The fifth energy level can hold a maximum of 18 electrons. The sixth energy level can hold a maximum of 32 electrons, and the seventh energy level a maximum of 32 electrons. And if we add up all these numbers, as already mentioned in a previous lesson, it will add up to 118, which is the total number of elements that exist. So if I had to ask you, in which energy level are the outermost electrons of chlorine? Well, all you have to do is look at the period number. And chlorine exists in period 3. So you can therefore tell me that the outermost electrons, or the valence electrons of a chlorine atom, exist in the third energy level. If I had to ask you, in which energy level are the outermost electrons of tungsten, which is W over here, well, you would look at the period number. This is period 6, and you'd be able to tell me that the outermost valence electrons of a tungsten atom exist in the 6th energy level. If I had to ask you, in which energy level are the outermost electrons of tin, Sn over here, then you would look again at the period number. It is in period 5, n equals 5. That tells us that the outermost electrons of a tin atom are in the 5th energy level. We also need to be aware of the fact that the first 2 columns, group 1 elements and group 2 elements, their outermost electrons exist in an S shell of their particular energy level. Group 13 to 18 elements, their outermost electrons exist in the P shell of their particular energy level. We only go as complex as the S block and the P block. We just need to be aware that group 3 to 12 elements that make up the D block, well, that means that their outermost electrons exist in a D shell. Now, metals in the D block have a name known as transition metals. And elements 57 to 71 and 89 to 103 at the bottom of the periodic table, they make up the F block, and that means that their outermost valence electrons exist in an F shell of their particular energy level. This over here forms part of the 6th energy level, and this period over here forms part of the 7th energy level. So in terms of the block groupings, we are only really interested in elements in the S and P block. You will see soon that we need to be aware of some important elements in the D block as well. But again, we don't work with the actual D shell or the F shell. We're only focused on S and P shells. All of this might sound confusing now, but by the end of the section, it will make a lot of sense because there are many, many diagrams coming up to help us clarify this. If I had to ask you about hydrogen electronic structure, well, you'd be able to tell me that hydrogen's outermost valence electron exists in n equals 1, which is the first energy level. And you would also be able to tell me that hydrogen's valence electron exists in the S shell of the first energy level. So it exists in the S shell of n equals 1. If I had to ask you about beryllium, you'd be able to tell me that beryllium's outermost electron exists in the second energy level in n equals 2 within the S shell of the second energy level. If I had to ask you about chlorine, you'd be able to tell me that chlorine's outermost electrons exist in the third energy level, and specifically they exist in a p shell within the third energy level. If I had to ask you about lead, you would be able to tell me that lead's outermost electrons exist in the fifth energy level in a p shell. If I had to ask you about vanadium, you would be able to tell me that vanadium's outermost electron exists in the fourth energy level in a D shell. If I had to ask you about uranium, you would be able to tell me that uranium's outermost valence electrons exist in the seventh energy level in a P shell. Let's zoom in to each group, starting with group 1 elements. Group 1 elements have a special name. They are known as alkali metals. Hydrogen is in group 1 and it is not a metal, but all the other elements are metals. Now, the name comes from the fact that when these metals or their oxides, for example, lithium or lithium oxide, are dissolved in water, then it results in a solution that is a base. A base is the opposite of an acid, and we use the word base or alkaline almost interchangeably. Alkali metals are highly reactive, and because they are so reactive, they are found as compounds in nature. They are ionically bonded to other elements, which we will understand in more detail a little bit later. Let's consider group 1 elements. We're going to consider hydrogen, lithium, sodium, and potassium. A hydrogen atom has 1 electron in total. So what that means is that hydrogen has 1 valence electron in the first energy level. And what do we call that first energy level? It is called n equals 1. So hydrogen's valence electron exists in n equals 1. The first energy level can fit how many electrons? Well, we learned that n equals 1 can fit a total of 2 electrons. Remember that all atoms want to have a full outer energy level in order to be happy, in order to be in their lowest energy state. Therefore, to have a full outer energy level, hydrogen can gain an electron or it can lose an electron. Of course, if it loses an electron, then it is simply a proton. And if it gains an electron, then it is going to end up with an outer energy level, n equal 1, that is full. So to have a full outer energy level, hydrogen may lose 1 electron. And if it loses this electron and it remains as just a proton, then it forms the ion H plus because it has a single positive charge. If it had to gain an electron, then it would become an H minus because it has 1 extra negative charge. Now, hydrogen's a bit of an anomaly. The other atoms can't just either gain or lose an electron. So you will see that all the others don't behave in the same way as hydrogen. So lithium has 3 electrons. What we can see is that its first energy level, n equal 1, is full, and in its second energy level, it has 1 electron. So lithium has that 1 valence electron in the second energy level, and the second energy level is called n equals 2. The second energy level, as we already learned, can hold a maximum of 8 electrons. So to have a full outer energy level, lithium is not going to gain 7 electrons. That is just too much work, too much energy. Lithium only has the potential to lose 1 electron. So when lithium makes an ion, when it becomes a charged atom, it becomes lithium plus, Li plus. That is the only ion that lithium can ever make because lithium only has the ability to lose that 1 electron. It doesn't have the ability to gain 7 to have a full outer energy level. It can only lose that 1 to have a full outer energy level. Once it has lost that 1 electron, well, its core electrons, they can't be lost. Core electrons don't ever get involved in bonds, and core electrons remain stuck to the atom. Let's look at a sodium atom. Sodium has 11 electrons. So the first outer energy level, n equals 1, is full with 2 electrons, and n equals 2, the second energy level of sodium, is also full with 8 electrons. And then we have the third energy level that has the 11th electron. So this means that sodium has 1 valence electron in the third energy level, which is n equals 3. The third energy level can fit a maximum, again, we learned, 8 electrons. And so to have a full outer energy level, the only option sodium has is to lose that 1 valence electron, and so it becomes Na plus. What that means is that the only ion that sodium can make is Na plus. And let's look at potassium. Potassium has 19 electrons, so its first outer energy level is full with 2 electrons. Its second outer energy level is full with 8 electrons. Its third outer energy level is also full with 8 electrons. And the fourth energy level carries the 1 valence electron that potassium has. So this means that potassium has 1 valence electron in the fourth energy level, which is n equal 4. The fourth energy level can fit a maximum of 18 electrons, as we learned. However, to have a full outer energy level, potassium has one option, and that is to lose one electron, its valence electron, and it forms the ion K+. So I hope that you can start to see the pattern. Let's consider the electron configuration. Let's consider this pattern that we see in all group 1 elements. Hydrogen's electron configuration, as we already learned in a previous section, is 1s1. So this shows us that hydrogen's outermost valence electron is in the s shell. Now, if hydrogen loses that valence electron, all that's left of it is just a proton. And if hydrogen gains an electron, then it will form the H- ion, because now it's got an extra negative charge relative to the number of positive charges that it has, only one. And so its electron configuration will become 1s2. That does not change the fact that it is a hydrogen atom, because remember that what identifies an atom as itself is the number of protons, and the number of protons is not changing. All that's changing is the number of electrons. That doesn't change the identity of the atom. That just allows the atom to get involved in chemical reactions. And what we can see is that the electron configuration 1s2 is the same electron configuration as helium, which is a noble gas. And we're in fact going to see that all atoms, when they become ions, end up with the electron configuration of a noble gas. Think of the noble gas as the cool kids. Everyone wants to look like the cool kids, so they can dress like the cool kids, but at their core, they might not be the cool kids. Their core doesn't change, but they're just trying to look like the cool kids on the outside. So the protons don't change, but the electrons do. Lithium's electron configuration is 1s2, meaning that the first energy level is full, and then 2s1. And again, that shows us that lithium's outermost valence electron lives in the s shell. Remember that all our group 1 elements are in the s block, and that's because their outermost valence electrons live in the s shell of their particular energy level. If lithium loses its valence electron, it will form the lithium plus ion, and again, its electron configuration will be just like helium's. It will be the same as a noble gas because everyone wants to look like the cool kids. Sodium's electron configuration is 1s2 because the first energy level is full, 2s2 2p6 because the second energy level is full, and then its outermost valence electron exists in the s shell of the third energy level. So again, this shows us that sodium's outermost valence electron is in the s shell, which applies to all group 1 and in fact group 2 elements. If sodium loses its valence electron, it will form the Na plus ion, and it will lose this 3s1. So its electron configuration will be 1s2, 2s2, 2p6. And note that this is the same electron configuration as a noble gas, neon. Again, the electron configuration of ions is always going to look like the electron configuration of a noble gas. Potassium's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, because in potassium's case, the third energy level is also full, and then the outermost valence electron sits in the fourth energy level, again in an s shell. If potassium loses this valence electron, then we lose this 4s1, and we end up with this electron configuration, which is identical to argon's electron configuration. Again, the same electron configuration as a noble gas. So here are some very important things that we can note from what we've just learned about group 1 elements. Firstly, all group 1 elements have one valence electron. Secondly, group 1 elements tend to lose that one valence electron in order to have a full outer energy level. So group 1 elements make a 1 plus ion, Li plus, Na plus, K plus. So that means that group 1 elements have a valency of 1 plus. Our exception is hydrogen that may gain or lose an electron. So hydrogen may form a 1 plus or a 1 minus ion. Thirdly, all group 1 elements have their valence electron in an S shell, in the S shell of their outermost energy level. Why do group 1 elements tend to lose 1 electron rather than gain 7 electrons? Well, that's because it takes less energy to lose 1 electron than to gain 7 electrons. It is not an option for these group 1 elements, except for hydrogen, to gain electrons. They will always lose their 1 valence electron. These atoms only need to lose 1 electron. They are therefore highly reactive because losing 1 electron is relatively easy. Another very important thing to note is that any ion of a group 1 element, and in fact any ion of any element, will have the same electron configuration as a noble gas. So this applies to all ions. All ions have the electron configuration of a noble gas because a noble gas has a full outer energy level, and ions become ions. In fact, atoms become ions in order to have a full outer energy level. Let's take a look at patterns in group 2. Group 2 elements are called alkaline earth metals. The name comes from the fact that when these metals or their oxides are dissolved in water, a basic solution results, and these metals are called earth metals because they are very commonly found in the crust of the earth, like calcium and magnesium especially. Group 2 elements are also very reactive. Now, we saw that group 1 elements are very reactive because they have to lose 1 electron, and we're going to see that group 2 elements are very reactive also because they have to lose 2 electrons, and losing 2 electrons is also not very energy intensive. Group 1 elements are generally more reactive than group 2 elements, exactly for this reason. So let's take a look at beryllium, magnesium, and calcium as our group 2 elements. A beryllium atom has 4 electrons, so we can see that its first energy level is full, and then it has 2 valence electrons in the second energy level. So that means that beryllium has 2 valence electrons in the second energy level, which is N equals 2. The second energy level, as we have learned, can hold a maximum of 8 electrons. So that means that beryllium can lose those 2 electrons. But if it loses 2 electrons, then its charge becomes 2 plus. So beryllium can only form 1 ion, and that is the Be2 plus ion. Magnesium has 12 electrons, so its first outer energy level is full, its second outer energy level is also full, and then it's got 2 electrons in its outermost, in its third energy level. So magnesium has 2 valence electrons in N equals 3. This third energy level can fit a maximum of 8 electrons. So to have a full outer energy level, magnesium's only option is to lose these 2 valence electrons. And then it has a deficit of 2 negatives, and it forms an ion of Mg2 plus. That is the only ion that magnesium can form. Calcium has 20 electrons, so its first energy level is full, the second energy level's full, the third energy level's full, and so its two valence electrons exist in the fourth energy level, n equals 4. This fourth energy level can fit a maximum of 18 electrons. Remember that calcium is the most complex atom that we're going to consider. Now, calcium, to have a full outer energy level, will lose these 2 electrons, and it will become the ion Ca2+. So beryllium's electron configuration is 1s2, 2s2. So the first energy level's full, the second energy level's definitely not full. Only the first 2 electrons exist in the second energy level, 2 of 8. When we look at energy levels, we have to consider the whole energy level. We don't just look at the S shell or the P shell. Sometimes I find my students, they get confused with the fact that, well, the S shell is full, but that does not make it a full energy level. So this shows us that beryllium's outermost valence electrons are in the S shell. And remember that group 2 elements are part of the S block. If beryllium loses its 2 valence electrons, then firstly it will form the Be2 plus ion, and secondly its electron configuration will look just like helium's electron configuration, again noble gas configuration. Magnesium's electron configuration, well, we can see that the first energy level is full, 1s2, the second energy level is full, 2s2, 2p6, and then in the third energy level, yes, the S shell is full, but the energy level is not full. So there are only 2 electrons in the third energy level of 8. But it does show us that magnesium's outermost valence electrons exist in an S shell. If magnesium loses the 2 valence electrons, well, it will lose 3s2, and it will end up with 1s2, 2s2, 2p6, which is the same electron configuration as neon, again a noble gas. And here's calcium's electron configuration. This is the most complex electron configuration that you would be asked to give. Right, and we can see that the first and the second and the third energy levels are full, and the fourth energy level contains 2 electrons in the S shell. So calcium's outermost valence electrons are in an S shell. And if calcium loses its 4s2, meaning that it loses the 2 electrons from its outermost energy level, it will form the Ca2 plus ion. This will be its electron configuration, which is identical to argon's electron configuration. Again, a noble gas. Here are very important things that we need to note about group 2 elements. All group 2 elements have 2 valence electrons. All group 2 elements will tend to lose their 2 valence electrons to form a 2 plus ion, and that means that all group 2 elements have a valency of 2 plus. And lastly, all of them have their valence electrons in the S shell of their outermost energy level. Because these atoms only need to lose 2 electrons, they are very reactive. Note that an ion of a group 2 element will always have the same electron configuration as a noble gas, and that applies to all ions. In the next lesson, we'll move over to the P block and we'll discuss group 13 elements.